We're good to go.
Okay, so let's start the second session of the day. So we have contributed talks from several people. The first speaker is Rakhi. Please go ahead and start sharing your slides. So Rakhi will talk about the SCARS conference, which happened just last month. So the floor is all yours.
Thank you, Shruti. Hi, everyone. Yes, I would like to tell you a little bit about the SCARS conference that took place last May at CERN. And this was a place where we tried to get together researchers from a wide variety of disciplines to discuss environmental sustainability in computing. And you can see here in the left-hand corner that we had some support from a variety of organizations. Of course, CERN, which kindly agreed to host the conference, the European Molecular Biology Laboratory, EMBO, the Swiss Physical Society, some UKRI, and EU and Wellcome funding. So I'm sure you're asking yourself why the need for yet another conference on computing or on sustainability. Well, I'm hoping to share with you a little bit of the thoughts behind the thoughts that provoked us to get together to try and start organizing something like this. One of which, of course, is the increasing environmental impact of computing. As high energy physicists, which I think most of us are here, I think it was already obvious to us how much, what a large part high performance and high throughput computing plays in our research. But of course, this was even prior to the AI or the LLM explosion, which brought these sort of intensive computing tools to every computing device in every household. And of course, as a corollary of this, the infrastructure required to power and run these devices also has to expand in a similar way. And what you're seeing here is some statistics shared by the Central Statistics Office in Ireland, showing the growth of one measure, which is the metered electricity consumption by data centers between 2015 and 2024, in comparison with similar statistics for urban dwellings and rural dwellings. Of course, this energy consumption has to be seen in the context of the global energy situation. And this includes the volatility in energy prices caused by recent geopolitical sort of uncertainties. Not just that, but in the context of sort of decarbonization pledges, where we have to move global primary energy consumption from being predominantly fossil fuel based. We have to reduce this fossil component to zero by 2050. In the context of this sort of growing demand in energy, this will create an energy gap, which needs to be plugged somehow with some combination of carbon dioxide-free, sort of GHG-free production and energy savings or efficiency gains. And of course, this savings will become even more important as demand and supply pushes up energy prices in the near future, as sort of renewable supply struggles to keep up with demand in the face of decarbonization. But of course, energy use, electricity use, is just one aspect of the environmental impact of computing. So this is just sort of the use phase. But we know that computing has an environmental impact across the entire life cycle of from resource extraction for manufacturing, for production of computing infrastructure to materials processing and the actual final manufacture, distribution, to final points of use. And of course, at the end of its usable lifetime, the disposal of the equipment. And this is not just impacts on carbon or GHG emissions, but this impact runs the gamut from air emissions, emissions to water and waste, as well as GHG emissions. So what you're seeing here on the right-hand side is some, unfortunately, of necessity, dated data for the impact assessment for the production of a monocrystalline silicon wafer. So a very pure silicon chip of the type used by the computing industry to make microchips of every sort. And this is one of the very energy and resource intensive aspects, but only one of these for computing. And what we were seeing was conversations about these impacts were starting to take place, but they were unfortunately siloed by discipline. So whereas we all use similar computing infrastructure and tools, and this doesn't just mean sort of scientific and technical disciplines anymore, but extends all the way across to things like meteorology, digital humanities, medicine, medical imaging, really the entire gamut. We're all using the same infrastructure and tools, and we're starting to have these conversations, but usually in parallel tracks of conferences that are specific to our disciplines. So there's a very high risk that advances made in one discipline do not filter out efficiently to other disciplines, who then risk wasting both human and financial resources in reinventing the wheel, in a sense, and trying to find their own solution to similar problems. So the idea of this conference was to try and bring together all these experts from different and users from different disciplines, all under the same roof, to not just create a community of individuals with common interests, but also to exchange these ideas and to brainstorm together and to network. And for this reason, we decided to make this first instance a hybrid with only one node. So that node was going to be at CERN. And we got together a fairly diverse organizing committee. So you can see we had a representation from, of course, high energy physics and experiment, but also bioinformatics, theoretical chemistry, climate science, computing, etc. And to parallel this diversity of organizing committee, we had a diversity of attendees. So this is a selection, I think a fairly complete selection of our 150 attendees for the 2026 edition of Scarce. And they were a diverse bunch. So, so you can see we had fairly equal representation by career stage, from junior to senior, and by sector, we had 60% from academia, some people from education, a fairly big sector from government, intergovernmental organizations, industry, NGOs, etc. And if we break down by discipline, you'll see the usual suspects here at the top. Of course, it was hosted at CERN, so we had a fairly large representation of high-energy physicists. But not just that, we also had climate and environmental scientists, material scientists, computational biologists, social scientists, neuroscientists, digital humanities, etc. And these people, we asked them to travel to Scarce if they could for this initial session. And of course, this travel has an environmental impact. Here you can see the geographical distribution of our attendees and the average GHG emissions due to travel to the location. We had a wide a diversity of types of sessions as well in order to make the most of our diversity of attendees. We had discipline summaries where a representative from each discipline will give a brief high-level overview of the sustainability initiatives in their discipline. We had interactive sessions, demos of carbon monitoring dashboards, poster sessions. Of course, we had keynote talks, both from the technical side and also from the behavioral science side and community building side. We had an entire contributor track on community building, writing session to sort of put together all the ideas that were shared in the conference. And here's a selection of the contributed talks that were selected by our committee for awards. And these share a similar sort of diversity of sort of a range of topics. So going forward, we are working on a white paper with a summary of outputs from Scarce 2026. One of the many interesting things we learned from working with people and talking to people from different disciplines was that there seemed to be a significant enthusiasm for keeping this community going, and in particular for turning Scarce into a regular conference series. We still have to agree on the timing of the next edition, but we're thinking something like 18 months to 2 years from the first edition. And one of the things we are going to try and do, given the difficulties we had in reaching out beyond our specific disciplines. I mean, I think you can understand this, this sort of spam fatigue. It's very hard, given the number of emails that one receives, to really distinguish a predatory conference invitation from a real one, particularly if you don't recognize the email address that it's coming from. Is that we have to make a special effort to improve dissemination of this conference, for the next edition of this conference, across to try and reach even more disciplines than we managed for this iteration, and also to widen sort of the geographical scope of the conference. One of the ideas we had was to have an open call for participation, but again, dissemination of this open call will be of crucial importance. So if anyone here has any ideas for how we can improve on this edition for our next edition, I encourage you to please reach out. And I want to end with a little plug for Sustainable HEP Plus, which provided organizational infrastructure for the Scarce organizing team, and from which we drew several of the organizing committee members. Now, this is, if you don't know, this is a grassroots group that started right here at the Sustainable HEP conference, but the very first version of it in 2021. And what we do is we advocate for sustainability within high energy physics, cosmology, astroparticle physics, and beyond, both within our communities and outside our communities. We liaise with funding bodies, etc. We are the authors of a reflection document, which contains fairly extensive summaries of the environmental impacts that we have as researchers, and a fairly complete set of recommendations for how we can mitigate those impacts. And we have several ongoing projects, including sort of a community building effort for life cycle assessments in sort of research and technical fields, an ORCLA project, which is an open research lifecycle assessment database, so we can share in order to make lifecycle assessments easier and more accessible to all. Of course, we're planning the next edition of SCARES. We have a series of hybrid seminars on sustainability in HECAP physics, etc., and a few other ideas in the pipeline. If you'd like to find out more and get involved, I encourage you to visit our website and to reach out to any of us. Thank you.
Thank you. It's indeed very nice to see that there's so many participants and from different various fields taking interest. So in the interest of time, probably we will just take one question. So please go ahead. Okay, probably I can go before maybe people can also post it in Matrimo. So you said you had awards on the talks. On what criteria did you base these awards on?
So we had a fairly extensive list of criteria, and there were different posters and for the interactive sessions and for the contributed talks. For the posters, there were some obvious ones. We had lightning talks, so it was effectiveness of the lightning talk. It was the visuals of the talk slide and how enticing they were. There was the visuals for the posters, the organization of information, the attractiveness of the poster. And for the talks, there were similar equivalent criteria. And I forgot to mention that these actually came with prizes that was sponsored by the Swiss Physical Society. So it wasn't just prestige that was at stake.
Perfect, perfect. And I wish you all the best also for the next time's edition and hope to be present there myself as well. But let's see. And thank you again for the very nice stuff. So the next presentation we will have on the perspective of sustainability, sustainable recommendations from the European strategy. So Veronique, go ahead.
Yes, hi. So thank you very much for allowing me to speak at this conference. So yes, this is a sort of historical perspective to where are we with European strategy and specifically related with sustainability, of course. And I've added here in yellow that this is very much a personal perspective. It's to sort of make it a bit more in terms of from a human perspective, having gone through all these different things. And so, of course, I don't pretend to list exhaustive number of activities that are happening in this area. I have a fair number of slides, so some of them I'll definitely skip, and I'm keeping an eye on the very useful timer that's at the top of my screen now. So I don't think you need a reminder of why I'm speaking today from my very hot office, and I'm not sleeping very well, and this is very terrible, and unfortunately a lot of people will suffer very much from the current heat wave that is happening in Europe. So now jumping straight into the European strategy, you might remember this graph of the European strategy is all about setting up the strategy for particle physics in Europe over the next few years from whenever it is released. And there's typically quite a long process related with this. My personal journey in all of this actually started before this, but not that long before this, where I read the Noemi Klein This Changes Everything book when it came out in paperback, so around 2015. And this was really a shock to my system, where I've suddenly realized that we're really talking about civilizational collapse from this. And we are the chosen generation that might make a difference. So then fast forward to the European strategy. I was in the IBIS in Meyrin for some Atlas meeting, and I was thinking, this is crazy. We're talking about the strategy of particle physics. We need to write something and submit something that addresses those things. So by the December 2018, we had put something together, and then there was Granada. Then something happened in 2020, which sort of delayed things a little bit compared to the schedule here. So this input had, because of the page limit of 10 pages, had only 3 recommendations. They're listed here, sort of basic things about including criteria for the evaluation of energy efficiency, carbon footprint of particle physics proposal, and reducing those, and of course about travel, and then the rest was signature that we collected. This was also around the time then, fast forward to February 2020, where we created the Atlas Sustainability Forum. So that brought together a lot of the people that I then interacted with and sort of made friends with related with these questions. And then the European strategy update came back with sort of a small paragraph that I've sort of zoomed in there, where it says the environmental impact of the physics activity should be minimized. And actually, it highlighted this issue of making sure this is part of the approval process for any major project, and that alternatives to travel should be explored and encouraged. So we'll come back to that. 2021 was the start of Sustainable HEP, our conference we're at now. So this has been a great forum to discuss all of these things. Then on the other side of the pond, of course, in the US, we had the SNOMAS, which is similar to the European strategy update, which is, setting out the strategy and the priorities for the particle physics field, but from an American perspective. And so there was a community engagement frontier in addition to the energy frontier, the precision frontier, all of their frontiers that the Americans like to have. And so we were a subgroup of the community engagement frontier. And so we had an input. So again, you can see sort of similar names there, where we try to, again, put some recommendations. And then in the summary report that came out here, we had eventually the P5 presentation, which on sustainability had one bullet point, which said that HEPAP should be the one developing a strategy for particle physics. And so we waited with bated breath as to what that would be, and then nothing happened. And now, of course, HEPAP doesn't exist anymore. This is this other committee there. And so we're still waiting to see what that sustainability strategy is going to be. Around that time in 2023, we had, as we just heard, the very influential report from the HECAP Plus. So this was absolutely great and a very useful input to all these discussions. So there were lots of recommendations, lots of data, lots of really great use cases, and all of this about gas detectors, about all sort of things there that wasn't necessarily captured before, and monitoring emission and be visible and directly contribute to the energy and climate fields and all of these different things. And so, of course, the desire to really capture fully those emissions and energy usage there was discussed. And since then, we've also had all sort of useful tools. So I wanted to highlight the French France Level 1.5 to know your carbon footprint if you're working in a lab or an institution or in research in general, and all of these different things. One of the things that also happened around then, it was the start of the CERN Innovation Program on environmental application. This is exactly part of what we had been discussing in terms of making sure particle physicists get involved in sort of cross-disciplinary interaction, and especially with environmental application. So I've put here that in 2025, this has continued as well. around this time, we had the rise of LCA, so life cycle analysis. So very influential Arup report. So Arup is an engineering firm which really they did a very detailed assessment of the construction of CLIC and ILC. So that was really important. And then I'm jumping in time, but you will hear tomorrow from Ben a lot more about this. And the laboratory director group has also given lots of useful advice on sustainability assessment and LCAs and all of that. And so then it was time for a new strategy. So my personal opinion is that this came a bit early compared maybe to what we were expecting, because CERN needed some direction there from the community with respect to FCC and all of these things. So here's that was the updated timeline of these things. And so again, we sort of rallied together and started series of meeting and discussion to prepare a submission document that would talk about sustainability as input to this whole process. So we had lots of meetings and discussion. This was fabulous to sort of all get together and discuss what could be the recommendation. And this time there were lots of inputs on sustainability. So I'm just talking about mentioning this one here, but there were lots of inputs. So that was absolutely great to see how this has been growing. So here I'm sort of flashing some of those recommendations here. So of course, this very important need to have life cycle assessment for all these projects and have environmental reports from all laboratories, right? The European strategy is not just CERN, it's all European laboratories or universities that are doing particle physics. And also CERN, of course, with its leading role in Europe and in the world, should also hold itself to emission reduction beyond its current targets. So here we had lots of discussion about this, and so we wanted to make sure to send that signal, and also about F-gases. So we had a really interesting talk earlier about how those emissions from detectors, and especially gas detectors, are related with our emissions. And then, of course, communication and communicating and addressing the environmental crisis, how important that is. Computing, we just had a talk about this, so we did mention that as well. And then travel, of course, and food-related greenhouse gas emissions, and habitat diversity. So we had a whole set of discussion about this. So these were the recommendation. Around that time, I'm just flashing here one article that I wrote with my collaborator Ken on the sustainability and carbon emission of future accelerators, and we included in there a discussion of negative emission option, including direct air capture. And then finally it came out. And so we had, as Jan mentioned earlier, 3 pages in the final brochure, the very sort of flashy brochure on the European strategy. There was also a sort of a companion document which fleshed out a little bit more those pages there. So if you have a look there for the working group. And what is interesting is there's quite a lot of, well, there's, comes quite some meat, not just in the sort of blue recommendations that are the final recommendation, but in the text around it. So for example, of course, civil engineering contributes a substantial way to environmental impact of major accelerator projects. And so this is saying, you see it there, that this might incur additional costs if you start looking for sort of greener alternative to, business as usual, cement and concrete and all of these different things. And so, so that's interesting to see this in writing. Formulate strategies for the environment and sustainability together in terms of their report. So something we had mentioned, educational framework, and then travel must be balanced against the environmental consequences. So there you go. And then again, on travel, should take into account the choice of venues for conferences, workshops, and meetings, and have So that's my last slide. So there you go, some personal thoughts on these. So well, one thing which is clear is that the recommendation don't go as far and wide as our submitted inputs there, but still they go much further than previously. So this is progress. On the other hand, the question now is whether they will be implemented. And again, a reminder, this is not just for CERN, it's for everything else. And so we have to hold those institutions to account. They are meant to be fulfilling the European strategy there, and we have to do individually our part. Just to give some example, ICHEP is in Brazil. So in terms of carbon footprint of conferences and meetings, Atlas just voted to have its Atlas meeting next year in Hong Kong. So, and we then the question becomes, how do we then close the loop of, we have some recommendations. If we don't think those recommendations are being fulfilled or followed, then what can we do about it? So there you go. So thank you very much.
Thank you very much again. So, okay, so I let people think, and maybe I had this question, but you already mentioned that so the recommendations are, so this is like an advisory or a recommendation thing, and people really need to implement it. So do you know to what percentage people, like different labs, actually implement all of those recommendations?
So, I mean, strictly speaking, normally our funding agencies in our respective countries, they are meant to be following the European strategy. So sometimes we've seen in the past that when we submit grant application, there will be some sort of text that says, make sure to tell us how your grant application follows the European strategy, right? So for example, when we think of, what to work on in terms of the flagship experiment, the top priority of the future experiments, and on the physics side, this is very important for funding agencies. So it is being followed from that point of view. And CERN is also absolutely, it's part of their mandate that they follow the European strategy. And so, it's absolutely possible to, if we think that CERN itself is not following those guidelines, we can say, and look, you're mandated from your constitution. I don't know exactly the legal standing, but it's definitely something that they have to follow. And that also applies to labs and universities, because essentially funding agencies of the CERN members are sort of supposed to be behind this European strategy that gets released.
No, that's extremely nice to know that they are actually mandated to follow things up. Jan, a quick question, and then.
Okay, and thank you for a very interesting talk. Coming back to this full history of how we try to make things better, and it's true, it looks like it's finally starting to bear fruit, although those fruits are still very small, I would say. But coming back to the latest update, so it's true that it's, as you mentioned, even including increased costs if necessary and so on, sounds like it's going in the right direction. But at the same time, the plan A is FCC, plan B is FCC, with no reduction of emissions whatsoever. And all we talk about is reducing emissions linked to the project we want to build, and not should we scale down the project we want. So how do you see this evolving?
Exactly. And so it's really up to us. I mean, at the end of the day, we're the ones who are going to build those detectors, those experiments, join those collaboration. And so it's about making sure that we're consistent with what we're saying. I mean, one of the many things that depressed me during, discussion related with the European strategy, especially related with this Plan B, was also that, China had been mentioning they would be interested in building CPC and all of this. And, the question was posed sometimes, well, let's say that China goes ahead with it. What does CERN do? I mean, and to me, it's so obvious that, the world can barely afford one such big machine, right? Even that premise, to me, I don't subscribe to it. I don't think we can, from an environmental point of view, we can't have one such machine. If China is, obviously we shouldn't have two. And in the spirit of collaboration and all of this. And then of course people bring in geopolitical concerns about, how this is problematic and everything. Well, I don't know. At the end, it's a question of priority. And so, all these things, I think at the end of the day, yes, people should sort of make sure that they are consistent and look at the big picture. It's not about reducing a project. It's looking at that project in the wider context. Can you even have it? It's not good enough to say, oh, we can reduce it by 20%. We can reduce it by 30%, those carbon emission. That is still too large potentially for some of these projects, right? So it's really important to get the broader context and not just what reduction you can bring in my opinion.
Thank you.
Thank you. I'm sorry, Henry, but could we please take this question offline because we
I'm
are
on Mattermost,
sure.
so if I've ruffled feathers and you completely disagree, that is also the point. So thank you.
Thank you very much, Veronique. So let's move ahead to the next talk on Nikhef sustainability roadmap. So Catharina, please, the floor is yours.
Hi, thank you. So my name is Catharina, I'm Sustainability Officer at Nikhef. We started out in 2020 with a partial scope 1 and 2 CO2 footprint analysis and focus on our high impact makers. But to reach our set ambition to become CO2 neutral in 2030, we had to change the way we approach this. So in this talk, I would like to show you how we are approaching this and embedding sustainability into the way our institute operates, and increasingly also into the way we conduct our research. So we really want to integrate sustainability into the way that Nikhef does her research. We see this as a two-way street. So first off, we really want to focus on scientific excellence because that is what we do. But also, how can we do this now, but also for future generations? So it's really this case of balancing. How can we make the environmental responsibility that we have to increase this, but also still focus on our scientific excellence? So we want to really embed sustainability into our strategy and the way that we do things. So we created a roadmap, which will be a journey rather than a single project. So the past few years, we really focus on doing projects like a travel policy and like small steps. But to really, over the past years, we really gradually moved from individual sustainability initiatives towards a more structured approach. So today we're focusing on creating the governance, the tools and the organizational culture to make sure that sustainability becomes part of everyday decision-making. And this roadmap really helps us move forward from ambition to lasting impact. So I'm not sure if it's really visible up close in the presentation, but I'll highlight a few key things that we do. So the gray area on top is how we are going to measure this. So it's a CO2 footprint that we will do every year and that we are setting up again. So as I said before, we did like the scope 1 and 2, but now from this year on, we are making a base footprint of scope 1, 2, and 3. I want to iterate this based on the biggest impact makers. Then the yellow block is saying that the how we are going to do this. So low-hanging fruit, but also big impact makers. We also know that the data center will be a big one. So that is something that we are already focusing on, also because of the issue of net congestion that we're having at our site. Then the blue block is focused on really communication and behavior. So how can we make sure that everyone within Nikhef feels responsible to contribute to lowering our CO2 footprint, but also thinking how they can make like positive impact instead of just having the feeling that we are going to take something away from them. And the third block is based on the strategy, because it was great that for the last strategy that we had like 2 or 3 pages in it that really focus on sustainability. But if you can rip it out, it was not there. So how are we really going to embed it in our scientific agenda and strategy? So how are we going to organize this embedding? So we coordinate it centrally, but we implement it and it needs to be owned throughout the entire institute. So that is one of the important lessons that we've learned, is that it cannot be owned by one department or one person. So my role as a sustainability officer is to coordinate, connect, and support people. But implementation really has to be shared across the institute. So we have the program leaders that integrate sustainability into their own domains. So what can they contribute within their own program? Then our sustainability ambassadors, who we have within each scientific and technical program, will help us raise awareness and stimulate the local initiatives. Then we have a strategy group and our directorate, and they provide direction and ensure sustainability remains embedded in our organizational strategy. And at the same time, we actively collaborate with NWO, NWI, and the sister institutes to really learn from each other and develop common approaches where this is possible. Then how do we start engaging Nikhef? So governance alone is not enough. Real change really happens when people become engaged. So we therefore invest in 4 complementary elements. So we do awareness. So in June, we had our first sustainability week, where every day we embedded an activity, workshop, or lecture about different topics. So people could choose to be there, but it's not like disrupting their entire day. We send out mails, we held interviews. So without it being like very in the face, we really try to make sure everyone knew that it was happening. Throughout the year, we have the community. So we have WIDE at Nikhef, which stands for Wellbeing, Inclusivity, Diversity, and Ecology. And every month, we really want to focus on these topics that has a lot of overlap to see where we can engage in people to become part of moving forward and the initiatives that take place there, and learn and exchange ideas. We're also creating a shared framework at the moment so everyone knows how to contribute. So this is going to be like pillars, travel, food choices, stuff like that. Because not everyone will feel motivated to contribute to everything, but one of them should be enough to contribute. And we have, with communications department, we focus on the visibility. So we have a website to really inform and inspire people, and also keep people in the loop. So small things like changing around the fruit that we have to local biological fruits, the tea bags, how we are changing up the light intensity to save energy, stuff like that. It's like small things, but it really shows that you are doing the things that you should be doing. Whilst not, just like it's a balance to find, because we don't want to greenwash or be like, oh, this is all we're doing, but make it like visible so people can see it. To make impact, so engagement should ultimately lead, of course, to measurable impact. So we started with areas where we can directly influence our environmental footprint. So For example, since travel was one of our biggest CO2 emitters, we made sure that policy carried out to change airplane travel that was carried out by the Institute. We organized a workshop where everyone could participate in creating this new policy, and that made sure that it was really embedded throughout the company and everyone really wants to contribute and also keeps each other accountable for this. So we now have a travel policy that encourages more conscious travel choices while recognizing the importance of still having international scientific collaborations. And next up, we're also working on improving the energy efficiency of our data center facilities and computing infrastructure. And these may seem like operational topics, but they provide the foundation for really embedding sustainability more broadly across the Institute. And over time, really also closer to our scientific activities. So we see it not as a project with a fixed end date. We make it an ongoing process of learning, improving, and working together. So it begins with ambition, grows through collaboration, and really becomes reality through everyday action. So that was my talk. Thank you, and I'd be happy to have your questions.
Thanks a lot. It's super nice to see that, as we heard from the first speaker, that the first thing we need to do is acknowledge the problem and just speak about it. And you guys are implementing this also in your personal footprint and being so aware of it on a personal level. And that really creates such a nice difference. It's very, very good to see that. So thanks a lot. For questions, I see Mathilde.
Yeah, hello. So first of all, thank you for your presentation. Really very interesting. I'm Matilda and I work with the ENFN. So as well with the ENFN, we are trying to address sustainability from like level 0 to kind of a process. So I don't know if you really mentioned this, but do you have already, or are you planning to have a sustainability report like GRI to put together like how you address sustainability and yeah, what do you think about if you have some key challenge in addressing like the reporting part?
And so you mean like official reporting part or inspiring or?
No, yeah, the official, like when you, for example, if you, I mean, the GRI standard for reporting are kind of the most famous, and then if you want to have this for your institute, then you have to follow a specific procedure. So I think like I'm questioning if you are thinking to have this or are planning to have this.
So in the Netherlands, we as an institute, we don't have to yet make a official reporting. We do have with our with the NWO, like the organization that Nikhef falls within. So we are doing the voluntary CSRD for so it's the VSME it's called, which is based on the Greenhouse Gas Protocol and the Science Based Target Initiative. So that is the reporting that we will focus on. But since we are not, we don't officially have to yet, it's nice to really can see where we can make the biggest impact with the institute and not just solely focus on the compliance and the reporting yet.
Okay, yeah, thank you.
Thank you. And yeah, I think it's also nice that Mathilde picked this up. I mean, at some point in the future, if everything goes well, I think it would also be nice to have a report so that other national institutes on a national level can also pick it up at some point in the future. So it's great.
Yes, of course.
So I don't see any more raised hands. And you're also very perfect with the
Good
timing and
timing.
everything. So yeah, perfect. So thanks again.
Thank you.
So yeah, so we can move to the last talk of this particular session. So William, please start sharing. So William will talk about the ULISSE project, which is how CERN can recycle their waste heat.
Wait, please wait.
No problem.
Okay. So can you see my my PowerPoint now?
No, you need to share your screen. So sharing, just go on the bottom of the Zoom.
Oh, sorry.
And there is a share.
Yeah. Sorry. I don't know what happened. Don't work.
Shall I share it for you?
Maybe. I loaded on my contribution.
I saw.
Yes, it's the PowerPoint. If you can load it, maybe. Yes. Okay.
Can you see it? Okay, so
Yes,
you can just tell me to go to the next slide and I'll shift slides for you. Don't worry.
Thank you. Okay. Because it's a in 10 minutes is very short to explain such a big project. Also because it starts with my master thesis in 1995, so it's 30 years ago, but it concerns just the CERN waste heat recycling. But today, 5 years ago, I have the opportunity to go further with this project with the funding from the Swiss Federal Office of Energy. And the results of the project were very encouraging. And now today, I think it's time to try to go back to CERN and to tell him that the ULISSE project is really a project that can really it's an opportunity for CERN's waste heat large-scale recycling. Okay, can you the next slide, please? Okay. Of course, everybody here in the community, you know everything about physics and so forth, but the more basic logistics and supply like water and energy, it's a more basic question, but very important and for everybody and also for a big facility like CERN. And so if we see last time with LHC in 2024, the CERN consumed about 1.3 terawatt-hours electricity and close to 3 million cubic meters to cool these facilities. And then you must remember that if you think that for each terawatt-hour electricity that you produce, maybe with the nuclear power plant, you need 2.5 million cubic meter water to cool your power plant. So we must maybe also to integrate this water consumption just to produce electricity for CERN. Voilà. In the future, with the high energy LHC in 2030, we can reach about 2.5 terawatt hours, 3 million cubic meter. And so we go further in 2040 with maybe the FCC, then reach to 1.8 terawatt hours and so forth, and 2070, maybe close to 4 terawatt hours, and how much million cubic meters of water, that's another question. In fact, of course, all the electricity of the facility finally is converted in waste heat. And the question is, how could we recover waste heat in the summer operation? Because normally the annual shutdown of CERN is in winter. And how could we use this waste heat in the winter, and that will be indirectly reduce the electricity of our electricity consumption of the facility? Okay, next slide, please. Okay, then the solution could be, in fact, is we need in fact, a seasonal heat storage. And an original heat storage system is to use the lake. And CERN is close to the Lake Léman, of course, the biggest lake in the Swiss Alpine region. So it could be a possibility to store during the summer the heat from the CERN and recover it in the winter semester to furnish the heat for cooling and heating services. Next slide, please. So here you have an idea what like who is such a sublake heat storage facility. Here you have typical 1 million cubic meter of water volume. It is just a self-sustaining insulated envelope. It's strong anchored on the lake bed, and it's such a storage facility have a capacity of about 23 gigawatt hours of electricity, with just 20 degrees difference between their surrounding lake. Okay, I go further because the time goes fast. The next slide. In the CERN's FCC feasibility study, they examine also the possibility to feed in its cooling water in the Genilac network. And Genilac is actually the biggest thermolacustrine network from Geneva, who the idea is to cool in the summer and to heat in the winter with water from the lake. The basic study of the ULISSE project I was made with the case study of the Genilac. And so I have seen that there is really a possibility to integrate, to boost, in fact, the Genilac system with the ULISSE system, seasonal heat storage. Okay, go please. The next step, slide, please. Here you have you can imagine what that means. Seasonal heat storage typical for Genilac. Genilac normally they will furnish about 250 gigawatt hours of heat during the winter semester, and we can do that with the help of ULISSE. And so in case that the Genilac bring to the consumers water on 6 degrees, they can bring it water and close to 20 to 25 degrees, and that boosts completely the coefficient of performance of the heat pumps to heat up for the end users. And so you can save a lot of electricity in the winter, and that is in fact the big challenge for our energy transition for everybody, every country, is how we must have enough electricity in the winter, because the electricity we need for the mobility, for the heat pumps and so forth, and the decarbonation of the industry. And Switzerland typically the forecast for 2050, they have forecast a lack of about 20% of the electricity during the winter. And so that was in fact the idea of the ULISSE project, funded by the Swiss Fellows of Energy, that ULISSE could help for about 30% of the Swiss winter electricity, like about 3 terawatt hours, which is enormous contribution. Please, the next step, next slide. Okay, I go further. This is just in comparison with the performance of the heat pumps of the Genilac system, normal with cold water from the lake, and then you see that typically during the winter they need 80 gigawatt hours to supply the heat pumps and the pumps to circulate into water through the Genilac system. And the next slide, if you do it with Genilac, the next slide, please. Then you double the cups of the system. You go from 3 to 6 performance, so that you in fact you divide by 50%. You divide your electricity bill by 50%. So just for Genelec, you save 40 gigawatt hours of electricity. That is the basic idea of the ULISSE Corsair. And now we can, in fact, integrate the waste heat of CERN in this system. Maybe can you go further, please? Okay, that is another application consequences because if you modify the temperature of the water, the drinking water means and so forth, they have a big impact on the electricity for the production of hot water, for the washing machines and so forth. Oh, okay, I go further because the time go far. Please. Okay, just the conclusion is that, in fact, with ULISSE, the seasonal sublake heat storage, CERN waste heat could boost district thermal lacustrine networks while protecting the lake against global warming. That means that half of the winter semester electricity consumption by TLNs could be reduced. They have also, what I explained before, have a big impact on the electricity that you need for domestic hot water production, washing machines, and so forth and so forth. If you apply to CERN about concerning 1 terawatt hour of electricity in summer semester operation, could in winter semester shut down, furnishing 80% or 800 gigawatt hours, because your seasonal heat storage have an efficiency of about 80%, which is relatively high performance. This was it, and so you can save about 150 gigawatt hours electricity by the end users. That means that about 15% of the 1 terawatt electricity of CERN is saved by the end users. And so you can make a balance. And so globally, if you integrate CERN in the region, you can say that by ULISSE, you can reduce, in fact, indirectly, the electricity consumption of CERN by 15%. Voilà. And what is an important aspect also is that in case of long shutdowns, and that is normally the big problem, because CERN have long shutdowns when the long shutdowns. Okay, you can the ULISSE reservoir, you can recharge it directly with heat from the lake, and just with a slightly lower temperature, 20 degrees in place of 28, you can also have a good performance of the system. So you don't need a backup heat sources of a boiler, and that is very important in question if you integrate all the investment requirements for this project. So actually, the ULISSE consortium for the advanced research phase, but that is now we are looking to build a consortium for the go further in the ULISSE project, and this advanced project is also followed by a pilot and demonstration system in 2030. And we are now looking for partners. And I think CERN is also invited to join the ULISSE consortium to explore his feasibility of integrating the waste heat from the future high luminosity LHC and perhaps the FCC. I thank you for your attention. Voilà. I stop there. I don't know if I speak.
Thank you.
Voilà.
No, I think it was perfectly on point. Thank you so much. Okay, so questions from the audience. Okay, so while people might be thinking and coming up with the questions, maybe if you could remind me again, when was the inception of this ULISSE project? You said that it was a long time back. Maybe I skipped the year.
In the beginning, yes, because I've made my master thesis at EPFL, and because I was at CERN and I had I've seen that CERN had a lot of waste heat, and I say, what can I do with that? And that was the reason why I make my master thesis about that. Okay, but at the time, that was not so big interest, because 30 years ago, the question about sustainability was maybe not a priority. So okay, a lot of time has go need to today. The questions is more important, and I think today the project is mature to go further, and why not? Okay, the ULISSE project that I was funded by the Swiss Federal of Energy. Okay, there was concerns the Swiss strategy for transition strategy for Switzerland, but in fact I don't forget that the waste heat and CERN can also integrate this project. And okay, that was the reason why I'm here today, and try to convince maybe the HEP community, and maybe to encourage maybe CERN to integrate, to participate in this project. Voilà. Sorry, I don't hear you very well.
I didn't. No, I was waiting, but like listening to your answer.
Okay.
Okay, no, this sounds very interesting, and of course, I will also give it a better look over on the slides, and hopefully, I can get back to you more questions offline.
Yes, I invite you and invite everybody. Feel free to go to my contribution, and there is a paper and report. We explain more in detail all this project, of course, that I cannot explain so in 10 minutes, of course. So you can find the PDF and so forth, and all the links to go further in depth to the details of all this project at different levels. So feel free to go there, and I'm very happy if people will discuss during this conference about the project, and voilà. I'm open for a lot for discussion, of course. Thank you.
Yes, thank you so much. Yeah, this was a lot of nice information, and I think it's nice that you have all of the information on the slide, so people, myself as well, we can go back and look at them in more detail. So thanks a lot, and hopefully continuing the discussion over email or Mattermost. So
yes.
Thanks again.
Thank you.
Yeah. So now I guess we can move to the last session of today. We have 4 talks. So we move to the computational aspects of today's session. So the first talk is on the open event gen. I am not sure who is presenting, but
Me
Rakhi,
again.
are you?
Yes.
All right. Go ahead.
Thanks, Josie. Hi again, everyone. Here I am speaking not with my scarce hat, so I'll take that off. And instead, I'm putting on my hat as a member of the LHC Reinterpretation Working Group to speak about a white paper that we released recently, talking about the sharing of Monte Carlo simulations for LHC event generation. So this is a fairly sort of specific case where the tools used to simulate these events are all open source and public. So these include things like Sherpa, MadGraph, PowHeg, Pythia, Herwig, and many others. I'm sure you've all heard of these or had a chance to use them. And these same set of tools are used by different groups of people to essentially generate the same set of processes. So, for example, Atlas experimentalists will use these tools to generate some set of standard model backgrounds and BSM signals, and then feed them to their own detector simulation. And CMS will do something similar, generate some subset of the same processes and feed them into their detector sim. And, the same thing is also done by different collaborations of phenomenologists. So for every collaboration or for every sort of BSM search, you would need to generate some number of standard model signals, standard model backgrounds and BSM signals. And here in this case, you pipe the HEP-MC events to some sort of pheno tools. So a sort of theorist level detector sim or a parametric detector sim like you have in Rivet. And then you have these analysis tools. So this event generation, there's a huge redundancy in this in the terms of the data sets produced and the infrastructure used to produce these data sets and to house these data sets. And that's not to mention the sort of human resources used to produce them. And these computing and this infrastructure and these resources obviously come with a cost. This cost is both financial, it has a financial cost, and it also has an environmental cost. And in this white paper, we tried to make an estimate of these. So starting with the financial cost, if we look at the generation and storage of some sort of benchmark number of HEP-MC events by, say, Atlas, and you find sort of similar numbers for CMS, here you can see a comparison in this table of generating these events over 2 years at a CERN tier 0 computing facilities, and the costs are in kilo Swiss francs, so thousands of Swiss francs, for compute, for storage, for egress, and for persistence. And you can see that these costs are really non-negligible. And this is, remember, for 13 billion events for one experiment. If you do this computation on a cloud computing network, the costs go up significantly, and you also pay costs for egress. So this is as sort of a private consumer, but you can also try to negotiate a public sector contract, which I think one of the experiments has tried to do, and this brings the costs down significantly, but still, it's still more expensive than running on CERN tier 0. So of course, this is not the cost of generating the entire event gen data set. The total annual event generation for Atlas is an order of magnitude larger. So you have to multiply all these numbers by an order of magnitude. And if you sort of project into the future, the statistics of Halloumi will require, again, another order of magnitude increase. And these financial cost estimates here do not take into account recent fluctuations or volatility in price of storage and chips brought about by sort of the increased demand from the AI industry. And one of the speakers at Scarce told us that HEP are going to become increasingly small and insignificant players in this market. And so our purchasing power is going to decrease. So in this context, it really makes sense to look at how we can minimize these computing costs in the future going forward. So that's financial costs, but also we tried to make an estimate of the environmental costs of this event generation. And of course, as I said in my previous talk, this is more than just GHG emissions. For the use phase, but for the purposes of this paper, we focused on the GHG emissions, predominantly because the embodied carbon is very hard to get reliable data for, because the processes, it's a very competitive industry, and the processes for production are really quite proprietary. And so this information is kept under close wraps by the industry and by the companies producing this hardware. So focusing just on the GHG emissions, we can break these down. We can look at the emissions per HEP-MC event as a standard figure, and we can break this down into use phase emissions plus embodied emissions, where the embodied emissions includes the emissions due to hardware and also the infrastructure housing the computing hardware, so say the data center. And the use phase emissions is roughly the compute multiplied by the power used per CPU second, multiplied by the grid carbon intensity, and multiplied by this power usage effectiveness. So this is just a factor that takes into account the overhead energy costs of the housing infrastructure. So say it includes, for example, the cooling costs of the data center that the computing equipment is placed in. So the figure of merit, taking into account some benchmarks, which I will explain to you in a minute, is 0.015 grams of CO2 equivalent per HEP-MC event for EventGen. And this is taking into account some sort of a benchmark server that is an Intel Xeon processor, one of the up-to-date, one of the modern processors with 64 CPUs. The PUE benchmark used was the average quoted for the worldwide LHC computing grid, so the infrastructure that these EventGen is carried out on. And the grid carbon intensity used was, again, for WLCG nodes across globally, weighted by the amount of EventGen that was carried out at each of those nodes. But it's very easy to scale this figure to change, to see how changing these parameters would scale this final result. So that's use phase emissions. We also tried to make an attempt to take into account embodied emissions. And we did this again using the same benchmark server that was used for the use phase emissions. And this one actually has an environmental impact sheet that comes with it that tells you what the total embedded emissions are for production. But of course, there are no details, and so it's impossible to independently verify these numbers. So we just took them as is. And using an industry average of 4 years for the lifespan of the server. And here the emissions are slightly smaller by an order of magnitude of 0.003 grams of CO2 equivalent per HEP-MC event. Just to note here that this is just the embodied emissions of the hardware and not of the housing infrastructure, so the total impact will be larger. And we can use these rough calculations to make an estimate of the total annual emissions for Atlas Monte Carlo event generation. And this is of the order of 2.4 tons of CO2 equivalent per year, which is similar to the emissions due to 1,000 transatlantic return flights. So it's not insignificant. And we expect that EventGen for CMS has a similar order of magnitude. Now, this is sort of a bit of a low-hanging fruit because just by producing these events only once and avoiding any redundancy of data and sharing these events so they can be used by other experiments, by any experiments and by phenomenologists, you have the potential to make a significant financial savings and environmental savings. And unlike many other discussions on environmental impact, here the financial and environmental savings don't pull in the opposite direction to physics, right? Because here you can make these savings without having a negative impact on the physics done. So it's a bit of a no-brainer. Indeed, this has been done by both of the main LHC, both of the largest LHC experiments, CMS and ATLAS. And on this slide, you can see a comparison of what each experiment has made available and how they've been made available. There are some differences. Essentially, the format of the events are slightly different. ATLAS events are released in HEP-MC2 format, which is compatible with downstream tools. CMS have made the choice of releasing, for now, the events in this sort of compressed format, which is tension sort of gains in a size, so it's a much more compact size, easily downloadable and usable at the cost of generality. But there is going to be a converter tool that is in the works from CMS-specific formats to HEP-MC3 format, industry standard, that is in the works and will be released soon. These events are available on the Open Data Portal. ATLAS data is partially available on the Open Data Portal. All the events are to be released on the portal soon, and they're awaiting an update by the portal staff. And you can access all of them using a Python tool that is freely available online called ATLAS Open Magic. In the white paper, we detail a number of interesting and relevant use cases for this open event gen. These run the gamut between comparison, increasing ease of comparison between different experiments and through increase of robustness and transparency of the data sets, designing VSM searches. So instead of generating standard model backgrounds for this, you can just download the backgrounds that are available and use these. For studying overlaps across signal regions for VSM models, for reuse and reinterpretation of standard model measurements. And there are many future interesting use cases, including jet RICO studies, unfolding of detector effects for jet RICO studies, machine learning studies, and training and education. We include in this paper interesting future directions, and there are a number of them that would be very useful for the community. I will leave this information here for future reference, but in the interest of time, I'd like to go ahead to the action items. We have a fairly long list of action items broken down by short-term actions, mid-term actions, and long-term actions. All of these will require engagement across the entire community, from experiments to sort of labs and institutions and computing groups, and also users. The part the users have to play is also very important here. One thing I would like to highlight is our long-term goal here, which has the largest potential for financial and environmental savings, and that is the centralization of LHC Monte Carlo production to a core team working in collaboration with generator experts and experimentalists. And this is a non-trivial undertaking. For historical reasons, the formats and the pipelines that the experiments are using are not common across the LHC, and so this is going to require agreement on common formats to start with, and also an expansion of the resources available for sharing event generation. So the message I hope I have put across here is that the open sharing of event generation can give rise to substantial financial savings and can and decreased environmental impact without a negative physics impact, and that there are also co-benefits in the sharing, in transparency, in reproducibility, and equal access, as it allows users who don't have access to the same computing resources or to the same expertise required to run these tools to access the data sets and use them. And these things will become even more important in the in the HiLumi era, as statistics increase, and it's going to be increasingly compute intensive to generate enough simulated events for these statistics, and also the generation becomes more technically involved. Now, ensuring the persistence of the open event generation that we have at the moment, and also to increase, to expand the offerings, will require significant commitment to provide dedicated infrastructure and human resources to maintain and expand these offerings. And this is where community uptake is crucial, because
I'm just sorry, but we are a bit over time, so just a ping.
Okay, I just want to emphasize the importance of community uptake. Here is an e-group you can join if you're interested in getting involved in centralizing event data. Please do think of use cases for this data, use and cite it. Thank you.
Thanks a lot, really. Yeah, so questions, please. Jan?
Yeah, so thanks for the talk. I was wondering, when it comes to common generation, for instance, between experiments and so on, given how many years each experiment spends tuning generators, adapting and making different choices, for instance, between Atlas and CMS and so on, how do you see the possibility of everybody converging all together and then producing something in common? I like the idea, but I'm a bit skeptical.
So that's a very fair question. And as I said, it's not going to be easy. But to answer, the only thing I have to say in answering that question is, when we suggested it, we weren't immediately shut down. So there are ongoing discussions on how to make this happen. One encouraging point is that even though standard data sets are made fairly differently in CMS and Atlas, there are, in order to take into account systematic effects, those parameters are varied. So the experiments use different generators in order to see, for example, theoretical systematic uncertainty. So there is a significant overlap between the event generation data sets already between the two experiments. So even eliminating that overlap or eliminating that redundancy for the data sets that they have in common would already be a significant first step.
Thanks.
Thanks a lot. Okay, I saw Chandramoli had but okay, and okay, so I also have some doubts, but for the sake of keeping a bit on time, we will try to address all of our questions to you over Mattermost. So thanks again for the very nice update. We go to the next presentation on reducing simulations related emissions through optimized event biasing. I can see you, Lachlan, whenever
I'll
you're ready.
share screen. Perfect. Okay, so hopefully you can all see my screen. Cool. So I'll start with a bit of background in the beginning, just since I know rare event searches are sort of a bit adjacent to HEP, to give you an understanding of sort of where dark matter direct detection searches are at the moment. We're sort of in searching through two frontiers. One of them, the sort of most explored at the moment, is this higher mass but very, very high exposure low cross section frontier, where a lot of the larger experiments in direct detection are exploring. And obviously with these really high exposures, lots of detector mass requires a extremely low background. And so the other side of things, we have this unexplored region in the lower sort of dark matter mass regime that, as I said, is unexplored at the moment. But being lower mass, we have much lower sort of nuclear recoil energies for our searches, and so that requires having very low detector thresholds, which again necessitates having extremely low backgrounds for our experiments. And because of that, our background simulations are sort of becoming increasingly computationally expensive. And one way to rectify this issue is to use event biasing, which is particularly useful for shielding studies where you might only have sort of 1 in 1 million events survive and reach your detector in a simulation. And so the question then becomes, how can we best optimize these biasing simulations to reduce our computational load and therefore manage our carbon footprint? So a bit of background on how biasing works in these situations. Again, it's just sort of variance reduction techniques which aim to just reduce the relative uncertainty of your simulation at the given computation time. The main process, so the main way that this works is that you aim to adjust the sort of statistical weights of your primary simulation events, such that when you combine them all together, they sum up to become the weight of some unbiased simulation. So you end up with higher statistics because you have a larger amount of these biased events with low statistical weights. But when you account for these weights, the results are sort of on par with what you would get for an unbiased simulation. There's a range of techniques implemented in JANT4 that do this, but I'm going to focus on the importance splitting / killing technique for this talk, since it seems to be the most commonly used for rare event searches in particular. So how does this technique work? It's a very sort of simple concept. You essentially layer your shielding or your detector volume or whatever you're simulating into, again, a series of layers, usually equal thickness, and you assign importances to those layers such that when you have a particle passing from one layer to the other, it gets split according to the ratio of the importance in the first layer over the next. In the case of particles that might go backwards, you give them a probability to be killed, which is just 1 over that splitting ratio. So in the case of an importance where the layers sort of have importances to the end, where they increase as you get closer to your detector, you can end up with splitting ratios of 2. So any time a particle crosses into another layer, as you can see in this diagram, it splits into 2 separate particles. One of them is original, and the other is a copy. And then if one were to go backwards, it has a 50% chance of being killed. In terms of the statistical weights, essentially they're given a weight by 1 on the importance value of the final layer that they pass through before interacting with your detector. And so you can essentially sum these up at the end of your simulation and get more statistically viable background rate. But the questions from users sort of come down to how do we keep account of different track / splitting topologies in your shielding? But and the focus of this talk is how do we optimize the exact layer count and maybe come up with some sort of general rule. So there was a study in the past to look at tracking topologies. I won't talk too much about this here, but I thought I'd mention it because it was really important to actually doing this study for optimizing the layer count. But essentially, anytime a particle is split, you assign a sort of independent, unique biasing index to the copy particle, and that allows you to keep track of all the independent topologies that exist in your shielding. And so I'd recommend checking this study out here from SuperCDMS on how exactly they were able to implement that. But the open question from this paper was how do we best optimize that layer count, as I said. So to study this, we used a sort of dark matter detector that we're working on in Birmingham, which is the dark sphere experiment. It's a gaseous detector of about 15 centimeters in radius, including the 1 centimeter thick copper casing for the detector. We surround it in 1.5 meter thick water shielding, with a cubic air gap between the shielding and the sphere. And essentially in a sort of separate geometry to the physical one, we have implemented these biasing layers such that they fill out the full shielding volume with equal thickness layers. So essentially the thickness of the shield should come up to the sum of every layer thickness. So assuming the layer thickness is equal for all of them. And we've used the sort of commonly used importance value of 2 to the n with a splitting ratio of 2 and a killing probability of 50%. To sort of understand where this optimal layer count might be, we've used a parameter of interest being the probability of interaction with our detector, which is just the sum of the weights detected in our sphere over the number of primary events. And then we use that with a sort of ensemble of different combined simulation jobs to derive what relative uncertainty, which is just the standard deviation of that ensemble over the mean probability from that ensemble, as I said. We then plot out this relative uncertainty against the execution time of these simulations and fit them with a power law to understand the trend for the computational efficiency. And so by comparing these two, these different trends for different layer counts, we can understand how they compare to one another in order to understand, what is the most effective number of layers to reduce our CO2 footprint. Our expectation for how these fits trend relative to each other is that at fixed times, we should have relative uncertainty decrease until reaching a minima at a high enough amount of layers that then it suddenly starts to increase. And the reason for that is that essentially the computational burden of doing the splitting in your shielding becomes sort of more so than if you were to simulate an unbiased equivalent amount of events. So we did this initially for photons at 2 energies, 2.75 MeV and 1.461 MeV. These were chosen because they're sort of common energies for backgrounds. In dark matter experiments, the 1461 here, in fact, is the potassium 40 decay line. And so we do sort of broadly see when comparing these fits the trend that we expected, but again, it's quite messy. And so to get around this, we take a fixed execution time, which was 300 seconds for 2750 keV and 100 seconds for 1461 keV, and we're able to pull out this parabolic trend that we predicted, where we've chosen the minima, even though the minima for both of these trend lines are quite broad. We've chosen the minima sort of directly in the middle to represent the optimal amount of layers. And in order to link it to physics for predictability, we've expressed the thickness of those layers at that layer count to be some multiple of the mean free path of a photon in water at the given energy. And we're able to find that, in fact, this multiple was about the same for both energies, and obviously corresponding to different layer counts due to the difference in mean free path at those energies. And so this means that we can predict that about roughly 0.45, 0.47 in water for photons is the optimal amount of layers, optimal layer thickness for your bias simulation. So we wanted to extend this to neutrons as well, because they're another common background source for dark matter searches that are quite bad for analysis because they're quite easily mimic dark matter. And we by repeating the same process again, we can see the same sort of broad trends when we compare the fits, and we're able to also pull out the parabolic trend in 2 energy cases at 10 MeV and 5 MeV. And we're able to find that at a different multiple of the mean free path of neutrons in water, we were able to get the sort of same behavior, which was that the optimal layer thickness was around 0.91 times the mean free path. So it's the same behavior, but different values for a different particle species. So these plots sort of show, we wanted to generalize this as well, because we wanted to see if it would change for different shielding materials and thickness. And we're able to pull out using the 2.75 MeV case for photons in water that are predicting based on the previous simulations that we would get a minimum about a thickness of 0.48 times the mean free path for both cases. We're able to pull out from our results that those predictions were relatively correct. And so using this, we're able to generalize to shielding material thickness. So it makes the results that we're showing so far more broadly applicable to wider simulations in the field, not just for our particular case. So I've talked a lot about how these sort of relative uncertainties perform at a fixed computational time, which was 300 seconds for the 2.75 MeV photon case. So for example, we were able to get 0.08 relative uncertainty at 300 seconds for the most optimal, and then 0.18 at 5 layers and 0.5 at 25 layers for the underbiased and overbiased cases. But what's important for this and managing our carbon footprint is understanding what our gain in the computational efficiency was. And so to do this, we do the inverse, and we have a set relative uncertainty, which was 0.08, and find that the optimal case, as I said, takes 300 seconds to reach that relative uncertainty. But for the underbiased case at 5 layers, it takes about 1,200 seconds. The overbiased case, it takes about over 5,000 seconds. And for the unbiased case, we're able to find that it takes sort of approximately 30,000 seconds just based on an extrapolation from our previous simulations. So that's quite a large difference in computational times, and so represents a large computational gain, but we want to obviously translate to a reduced CO2 footprint. To do that, we've taken this method from this paper here from Valerie Lang, where they've done the same thing for HEP experiments. I'd like to point out as well that, again, this is for these calculations in this plot are for experiments at the LHC. Cynical sort of criticism here would be that the computational burden to our emissions is much smaller than the experimental one, for example. But for rare event searches, we would actually expect that experimental burden to be much lower. And so relatively, this computational burden is probably much more of a problem for our experiments than yours. And furthermore, it's probably the one part of your footprint that you actually have real, besides travel, you actually sort of have real individual control over. So to calculate our footprint from this sort of reduced footprint from these computational gains, we combine the power usage effectiveness of our HPC cluster in Birmingham with the power consumption of the CPU cores we use in kilowatts with the workload in core hours, and then convert it to grams to a CO2 equivalent with this conversion factor, which is sort of grid dependent. And so the numbers that we used here for our Birmingham cluster are given on the slide. This 174 grams of CO2 equivalent per kilowatt hours was taken from a number from basically the UK grid's average carbon intensity. And we're able to find that for this simulation requiring a relative uncertainty of 0.08, we found that we couldn't achieve in comparison to unbiased simulations a factor of 100 improvement in the CO2 footprint, which is quite large. And you can see the cases for the underbiased and overbiased too, which are also quite relatively large factors. And also I'd like to note this is also calculated on a per core basis. So when you account for your full simulations, it's going to be a sort of much higher absolute footprint as well. So I won't go through the whole summary slide, but I'll leave it here. The main takeaway is that by using this method of trying to determine the optimal amount of layers for your biasing simulation, we're able to yield a factor of about 100 reduction in our computing carbon footprint. And if you poorly optimize, you can also lead to larger footprints too. So this is a very good sort of motivation for optimally choosing your layer count. And we're hoping to have this on the archive very soon as well. Thank you.
Thank you very much. That was super nice and super detailed. So we will take just probably one question. So yes, Henry.
So when you were talking about this, it sounded super like Hillis thinning from extensive air showers. Is this inspired by this?
I'll admit I don't know much about the simulation of air showers. It sort of from my research of this biosync technique has been around for a long time, but most of the work in sort of developing it has been in the field of nuclear physics, particularly for simulating dose rates for source transport and that sort of thing. So honestly, most of my inspiration for this has come from those sorts of studies. But
well, there might well be intersection because nuclear physics also uses the Fluker code, I think.
Yes, yeah, exactly.
Yeah,
yep.
yeah. Ah, that's cool. Yeah.
Cool. Thanks. So in the interest of time, I think if we have more questions, we should take it offline. And thanks a lot again, Lachlan, and we hope to read more of your preprints and papers. So with this, thank you. We move to our next speaker. Jiahui, please share your screen. And Jiahui will talk about energy efficiency of GPU-based computing system in high energy physics.
Hello, everyone. Can you hear me?
Hello. Yes, very well.
Yeah, this is Jiahui from ESUPP in Valencia. Yeah, I'm going as thanks for introductions. I'm glad to be able to talk about our recent research related to the energy efficiency of the GPU-based computing system in HEP. So let me just start. This is the outline of my talk. Since it's only 50 minutes talk, I will just directly start with introduction. So the whole research is done under the project called IDLE. It's the full name is the design of the high performance algorithms for the low power sustainable hardware for LC experiments and the upgrades. The PIs are the Lucas and the Arantxa. So this is our team. We have part of people from LCB experiment, another part from the Atlas experiments. So under this project, so we have a small isolated rooms in the EFIC experimental lab area with several racks installed to quantify the energy consumptions. And as you can see here, this is the room I'm talking about. And this is the infrastructure we have. So we have two machines with x86 as a framework, as a base. One using the Intel CPU, another use the AMD CPUs, and the several GPUs are installed in these two racks, two machines. And we also have a machine, it's not showing here in the photo, but using the ARM architecture. Additionally, we have APC, which is a power unit to be able to measure the power consumptions as a standard device. So, what we do here in this research is basically trying to focus on one of the experiments in a Large Hadron Collider. It is the LHCb experiment. As you see here, is one of the 4 Large Hadron Collider experiments. In this kind of experiments, we have a lot of computing requirements in the online system. We have to do the real-time reconstructions and to do the trigger decisions because the event has a very large multiplicity and occupancy. In fact, the LCB in ROS3 has to do real-time reconstruction 30 megahertz directly in the software. They basically reconstruct 1,800 million tracks per second. So this is how the trigger system of LCB looks like. So we have a GPU-based system. It is called ALIN. Basically, this system have to handle the 30 megahertz no-empty proton-proton collisions as the detector readout directly. So this is approximately 4 terabytes per second data flow. And the HT1, the system we called, has to reduce this data flow to approximately 100 gigabytes per second. So to be able to do that, we design this GPU-based application. Basically, the entire trigger is running in the GPU. So we pass load data from the host to the device and they process all the reconstruction and trigger decisions on the device and return the selection decisions back to the host. So this is how it works. I have to say LCB is actually the first LC experiment that used GPU-based system as the first step of trigger that directly output next to the detector readout. And it has currently approximately 300 GPU algorithms running. And the system is built on top of the 500 NVIDIA RTX 8000 for ROS3 data taking. So here is the link of the code of the repository. If you are interested, you can take a look. So the idea of the study is to study the energy efficiency of such a GPU system. So the first thing we realize is in HT1 of the HEP experiment is completely GPU bounded, which means with the same GPU but different CPU, we have reached the same performance in terms of throughput. So it is very natural to study what is the energy efficiency of the GPU. So what we do is we benchmark all these GPUs in these tables, including some GPUs from the Samsung 8 nanometer manufacturer and some of them from the TSMC 4 nanometer. So this is a list of GPU benchmark. We benchmark all GPUs across different architectures with different number of CUDA cores, boost the clock, memory bandwidth, and thermal design powered. So the way we do the measurement of the different GPU is to use the NVIDIA SMI to monitor GPU parameters in the plateaus. So basically, we launch the HT1 and we wait the parameters reach to plateau of the curve, and we measure the peak because we expect the HT1 to be run constantly in the data taking. So this is why we pick a plateau and not a run up or a run down. To cross-check these parameters, one of them is the power consumption. Of course, it's the most important one in this talk. We use the power unit I described before and the ACPI from the motherboard to double-check if the measurement is consistent. And of course, we make sure everything is consistent. We measure the power consumptions, CUDA core clock speed, and the memory frequency in these plateaus. So the result of these measurements looks like this, and we compare the measurement with the specification of the GPU by the manufacturer. And what we see is in the clock speed, usually the GPU can run above 5 or 60% over the specifications. So this is basically a boost mechanism. So when the GPU has thermal rooms and has enough power, it can run a little bit over speed compared to the specifications. Such thing doesn't exist in the memory, so we see a good agreement on the memory bandwidth between the measurement and specifications are consistent, more or less. We also measure the power consumptions, and one thing we realize is for some GPUs, the power consumption can reach to the Telma designed power, which is the TTP, the maximum power the GPU can deliver. Some of them cannot reach that maximum power. So we classify the GPU into two categories. We call the power limit GPUs. Without GPUs can reach 100% of the TDP. Those other GPUs called the no powers cannot reach the TDP in the HT1 application. Why this is important? Because later on we use these parameters trying to model something to be able to predict the throughput of HT1, which is the performance of HT1, and the power consumptions of HT1 in HEP experiment. So what we do is we use this simple model with the number of cores times clock frequency. This is basically the T-flop we talk about, and times bandwidth with different exponential factors. And the normalization factor, this is our throughput model in the left side. We also do the similar thing for the right side, but for the power consumptions. As we say, we have a power limit GPU and the no power limit GPU, so we use a mini model to describe that. So when the power on the demand, it is over the power, the maximum power, the DDP, the power total will be the DDP. Otherwise, it will be the power on demand. So we can describe the different type of GPUs in this model. Saying that, it is very trivial afterward to estimate the energy efficiency, as the energy efficiency is the throughput divided by the power consumption. With throughput, it's basically the number of events per source per second. The power consumption, it is the watt, the number of energy per source per second, consumed per second. So the division of this directly gives us the number of events per source per joules. So this is what we call the energy efficiency. So now our models of the throughput and the power consumptions can directly give us a prediction of energy efficiency across different GPUs. As you can see here, this is the result. So that has a very interesting part. First of all, we see the measurement and the predictions are different. That basically is due to the predictions made on the specifications of the GPU. The measurement is done directly with the measurement. The differences is come from the boost mechanism we described before. But you see even they are slightly different, it doesn't change the ranking of the GPU. So the GPU has lower energy efficiency, still have a lower energy efficiency for the prediction. So from this, we saw different interesting conclusions. The first is the fastest GPU is now the most energy efficient GPU. So you can see here the fast GPU has the highest throughput. It is the RTX Pro A6000. This is clearly not the most energy efficient GPU. It's actually in the middle of the graph. And also we saw the being power limit or not cannot determine energy efficiency because we saw some GPUs are reach DTP, some doesn't, but that cannot predict the energy efficiency. One example it is the RTX Pro 4000 and the RTX A5000, both are power limit, but they have very different energy efficiency. So which means energy efficiency is independent metric. It depends in the same time the throughput and the power consumption. So we have to measure it independently. And another fact we observe is once the two GPUs that have similar throughput, like the RTS 4090 and the RTS 6000 ADA, may have a very different energy efficiency. You can see they are ranked differently in the ranking. So which basically means we have to consider energy efficiency independently, and it's very important factor when the two GPUs we have to choose one of them. Both fulfill the requirements of the throughput. We should choose the one has a better energy efficiency instead of the one doesn't. All right, so this basically it is all content of my talk. That brings me to the summary. So as we see in this talk, the HEP project in the EFIC Valencia, it is the project under these studies. It is a project we do for the sustainability studies in Halloumi LLC. And the first takeaway of the talk is the energy efficiency is clearly an independent metric that not depends directly through throughput, but also depends on the power consumption of GPU. And we made a model that is able to predict the power consumption from GPU specification, so we can do the choice before we actually buy the device. And this methodology, it is not only for LCB-HT1. It actually can be extended to any GPU-based applications. And related to paper, it is now on archive. Here in this picture is actually clickable. You can click and see this is the paper we upload to archive. And the journal publications is currently in progress. And thanks very much.
Super nice and also perfectly on time. Time for questions, but yeah, I think we'll take a very quick question. Jan, or I don't know who was. Okay,
If
so
there
Jan
are
and then
others,
Chandramouli,
I've
or
already
maybe
asked
Chandramouli
questions.
because I took Jan's last time, so probably yeah.
Hi, can you hear me?
Yeah.
Yes.
So I noticed that you mentioned in the paper that it's the paper was specific to high energy physics, but the final results were not high energy physics specific. So why not publish a paper which is more general?
Yeah, this is a very good suggestions. Yeah, when we write the paper, we really just think about high energy physics experiments because we have very high throughput demand and the power consumptions always be kind of neglected in the community. So we put that. But yeah, I think this is a very good comment because the methodology, it is independent. This is for any GPU-based system.
Yeah, indeed a good, yeah. Okay, so for the sake of time, I think we'll go to the final talk of today. Thank you so much, Jiahui, for the nice talk. So we come to the final talk of today. Henry, whenever you're ready, please go ahead. So Henry will be talking on reducing compute use for calorimeter simulations.
Fantastic. So thank you everyone who stayed this long. I won't keep you too long. I'm going to talk about fast simulation for a HEP, and we've already had a lot of great introductions to all sorts of angles that we can optimize things in HEP. Fast simulation is one that we've been doing for a very long time now. So I'm going to open with a quick word on Jevons paradox, because I think the moment you start talking about generative machine learning, you have to take Jevons paradox into account if you're going to think about sustainability at all. Actually, out of interest, because this is quite central to this topic, how many people here have heard of Jevons paradox and kind of know what it is already? Like, yeah, cool. So some people here already see where this is going. So I'll start by talking about the what and why for a fast simulation, although some talks have introduced this very well already. Then I'll tell you about just one of the models that we used to do it. We've got a few models, but I'll focus on this one because it's the fastest one we have. And then I'll talk about some benchmarks and why those benchmarks are important when we're considering Jevons paradox, and finally conclude. So, Jevons paradox is basically this idea that if you make something more efficient to do, you make a process more efficient, it doesn't always lead to less resource use. In fact, sometimes, because we made it more efficient, more people can afford to do it, so it's more useful, so people do it even more than they did it before, to the point at which we have higher resource usage. And this was actually originally observed during the Industrial Revolution regarding coal. So coal usage, coal engine became more efficient, and that meant that you burnt less coal to do the same thing, but because burning coal was now a more efficient process, overall we burnt more coal because we built so many coal engines. We don't want to do this with fast simulation. We don't want to build a more efficient simulation program and just end up running so much more simulation that we end up using more compute cycles than we did before we had fast simulation. The aim is to reduce the total number of compute cycles. So why were we doing the simulation in the first place? Well, we were doing it to compare to data, right? So I don't really need to go too far into this slide. We've already mentioned that Atlas is recording 1,000 events a second. And to have a good statistical comparison, we normally say we need about 10 times the amount of simulated data as we have observed data, at which point the statistical uncertainties from simulated data are not the leading order uncertainty, so we don't care about them anymore. And future colliders only make this problem worse because future colliders contain more granular detectors, so the calorimeter being the really expensive bit to simulate, and they will have higher event rates potentially. So we need to find a fast way to do this. I did a back of the envelope calculation and realized that if you wanted to do all this in Monte Carlo simulation, and you had all the computers that are used to mine Bitcoin, you actually could. And normally in this talk, that's when I make a joke about starting a cryptocurrency, but maybe that's insensitive to this particular audience, so I'll resist. In particular, simulation proceeds in a number of stages, right? We have the hard interaction, super cheap, really fast. Also, the physics is important, so we don't really want to mess around with generative machine learning there. We have hadronization and showering. There are some really cool generative simulation works for hadronization, but they tend to be about improving accuracy rather than speed. But the slow bit, as has already been discussed, is simulating the interactions of a particle in a detector. That's anything from a minute to nearly an hour worth of simulation, depending on the granularity of the detector and the energy of the particle, which is just not feasible. So even if we're not thinking about sustainability problems, we still need to replace that. Okay, how do we do that? Our flagship model for photons specifically, we have other models for other particles, is this CalorClouds 3. CalorClouds 3 breaks the problem down into two parts. It says, right, you have a photon in a detector, and you have macro features, like how much energy gets deposited in each layer, what's the multiplicity of hits on each layer, and those you need to get really right. So we'll use a large, expensive model for modeling those. And then you have each individual energy deposit. And that doesn't matter so much. A photon shower is kind of like a fuzzy blob in the detector. There is internal structure, but only at very low energies, and it's not very significant. So we can do this fuzzy blob very, very fast if we consider every point completely independent and we don't allow them any communication. We impose the macro features that the normalizing flow has requested, and then we use a diffusion model that treats each interpoint as drawn from an IID distribution. And this does give us some pretty accurate photon showers, actually. Here are the 3 standard plots for looking at a photon shower in the detector. So on the left here, we have the spectrum of cell energies. So in each cell of the detector, if we add up all the energy deposits, how much energy did that cell have? We histogram it. And we can see a mid peak, and we can see it tail off towards higher energies. And I'm plotting for you here the model reproducing this distribution at 3 different energies, because they're energies that we expect to occur quite a lot in a Higgs factory detector. And you can see that the model is marginally better at higher energies, not such a good performer at low energies. This is because of that IID assumption we made on the hit energies. Essentially, it's closer to a fuzzy blob the higher energy you go, because the details wash out in the number of hits. In the middle, you can see the radial distribution. So we expect most hits in the center of the shower, and then the hits will die off as we reach the edges of the shower. Again, we're modeling this quite well at 3 energies. And finally, you can see the distribution through the layers. This is the one that our normalizing flow is controlling, so it should be the best of our 3 distributions, because it's determined entirely by the more expensive model. And that's doing really well at all 3 energies. And the real reason we're using this model is because we can match the performance of Geant floor, as you can see here, and we can do it about 1 to 2 orders of magnitude faster on CPU. So here you can see that the higher energy the photon is, the longer it takes in Geant 4, and the greater the speed up we get from using a generative model to create this photon instead. On a GPU, we would get more like 3 orders of magnitude, but as GPU computation isn't always available in event generation processes, we tend to base our comparison on CPU computation, just to kind of like err on the safe side in terms of what this model could buy us. So, okay, this is all very well. I've shown you 3 plots that describe the model's performance from the perspective of energy of calorimeter cells, but that's not really what the model's used for. The model's going to be used for analysis. So we're going to do some benchmarks on analysis to decide how the model would behave in an analysis. And there are several metrics. The first one is the linearity. So for a given photon produced by the model, what kind of energy would we reconstruct? Hopefully this is a nice straight line if your calorimeter's been designed well, because you expect to model something that scales linearly with the energy of the photon. You can see a few other lines on those. Those form theoretical maximums for good performance based on our data pre-processing. And if we have a look at our model on this, it's really good. It's really close to the Geant 4, the full Monte Carlo Markov chain. We'd also have the resolution of the reconstructed photon. So that's a measure of how far from the truth you are when you're reconstructing photons at different energies. Again, if I impose the model on this distribution, we see that we follow the full Monte Carlo Markov chain behavior really well, which is the desired outcome always for a fast simulation model. And finally, we need to get the multiplicity of these jets right, because that's a core quantity in a lot of analysis. So we might take 2 photons and fire them into the barrel. And if we fire them in exactly the same position with exactly the same direction, of course, we will never distinguish them. So on the far left of this plot, where we've got no separation, we always reconstruct 1 photon. Then as we go along the plot and we increase the separation between the 2 photons, eventually we should consistently reconstruct 2. We need the showers produced in a fast simulation model to separate out, to have the same ability for reconstruction algorithms to separate them as those produced by the full Monte Carlo Markov chain. And again, at a whole range of energies, we see really nice behavior from this model. So this is great. And actually, I think this is quite important, not just from the point of view of proving this model is safe for use in analysis, but it's important from the point of view of looking at this model through the lens of Jevons paradox. Because anyone can build a bigger machine learning model. And indeed, we have got bigger machine learning models that produce more accurate representations of the cell energy spectrum, of the radial distribution, of all these things. And they are physically closer to Geant 4, but after reconstruction, we can't tell the difference. So that extra complexity that we could potentially inject into this model that would make it more realistic, it's actually useless. It doesn't bring us any closer to our end goal. And I think that end goal is really important if you're going to use generative machine learning for physics and you don't want to get caught in Jevons paradox, is you need to know when you start doing your simulation exactly what you're aiming for, and you need to know when you've reached that target so that you can stop. And we know what we're aiming for in terms of the number of simulations. Like we said, that's going to be 10 times the amount of observed data. But we also need to know what we're aiming for in terms of quality of simulation, because the larger the model, the longer it takes to run. So if we have a really good benchmark for reconstructing, and we can tell, is this simulation good enough for use in analysis, then we know when we can stop in terms of making the generative simulation larger and more accurate. And we have a proper finish line for when we're done using this kind of resource. Yeah, so in summary, machine learning can be both fast and accurate, and we need it to do any kind of physics at all. So there's no getting out of using this for modern high energy physics. But if we have the right benchmarking, we can use it more efficiently. We can ensure that we've optimized the trade-off between the complexity of the model and its fidelity. We'd like to benchmark more of our models so that we can tell exactly how low we can go in terms of complexity. We'd like to look at mixture of specialist models so that we can mix and match features of models for other particles that would allow us to use the most efficient technique for any given particle. And we'd like to look at transfer learning so that models can be used in situations that they may not have been trained for. Yeah, that's everything from me. Thank you.
Thank you. Absolutely on point with respect to time. Super nice. And yeah, the talk was super interesting as well. Very good summary as a closing talk for the day. And questions from the audience. Yes, Lachlan?
And so I'm assuming, correct me if I'm wrong, that the model, I guess, is sort of like detector dependent. And so I'm wondering, is it as simple as just sort of training it on data from another detector to sort of generalize it to a new detector, I guess, or is it a bit more complicated than that?
Yes and no. So the model makes a very strong assumption that your detector is onion skin layer style. And that's true for a lot of our detectors, but it isn't true for, do you know the Allegro detector design?
Yeah.
Yeah. So we've actually got a student right now who's working on transfer learning, and his problem specifically is that we can do transfer learning, which is when you say, right, I have a model I've already trained. I don't want to retrain it because I don't want to produce that number of training samples. I want to take a very small sample from another detector and just tweak the model to match this new detector. And we can get away with about 1,000 to 10,000 showers, depending on the fidelity of the detector, to tweak a model, which is much less than the dataset you'd need to train it. But Allegro is really challenging because Allegro doesn't have these onion skin layers. So the student's current work in progress, will hopefully be published soon, is what you do when you have a detector that's just got a completely different geometry and you want to use the same philosophy.
Okay, yeah, that makes sense. That's very interesting. Thank you.
Okay. Thanks a lot. So yeah, I think we can take up further questions and discussions on Mattermost. I think we are a bit late, but I'm very happy that we had a lot of discussions on all of the talks. Thanks a lot again, Henry. I know you have also been involved in discussions on Mattermost, which was super interesting. I'll go through in details later. So I guess with this, we come to the end of today's session. We have a session tomorrow again, starting at 2, and hopefully we'll see most of you there. So we have the plenary talk on the lab directors group recommendations. We have submitted contributions on compute again, the second session of compute tomorrow. So do attend that, as well as on detector and material development. And as a closing session, we have the panel discussion on people who have moved from HEP to other fields field of sustainability. So this is a panel discussion. You can ask questions. We have the Slido links already given to you. If you have any questions beforehand, you can already put them there. So yeah, with this, I guess all of you have a very good evening, very good night, and a very good day. So yeah, see you tomorrow. Bye-bye.
Bye.